Good morning, everyone. So we are starting 11.4 today. Before spring break, we left off with 11.3, where we were talking about if data was skewed or not. So today we're going to talk more about symmetrical data and some different things we can do with that. So excuse me. Today we're going to quantify and analyze the spread of data. Now you've done a little bit of this before. When we talk about the spread, we want to know how far apart the data points are. So we've actually calculated the range before. Range was the max to the min. Today we're going to talk about something called standard deviation. So this is 11-4 standard deviation. Okay, you got a formula in here that's going to take a little bit, so make sure you really pay attention and you understand what each of the symbols mean. Okay, so we're going to dive right into an example. So the makers of a certain brand of light bulbs claim that the average life of the bulb is 1,200 hours. The lifespan in hours of a sample of brand A light bulbs are shown. How close to the claim were the light bulbs in this sample? Okay, so we got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 20 data points. So what type of data display will provide the best view of the data? Well, when we've got numbers that spread out, we like to look at a histogram. So we are going to create a histogram for this model. Okay, so we're going to do a histogram. So when we're looking for a histogram, I always like to find the smallest value and the biggest, because to me that helps really decide how big our interval should be. So let's see, looks like maybe 1080. Do you see anything smaller? Okay, so here's my smallest. Okay, where's my biggest? Okay, I'm seeing 1345. It's my biggest. Okay, so I go from 1080 to 1345. So I'm thinking maybe we should go by 50s. Okay, so let's see. Make my histogram. Let me get some lines up in here. Send it a little bit. Okay, so we're gonna go by 50s. And I think I'll start at 1,000. Yeah, it's a fun. Okay, so we'll go 1,000 to 1049, 1050 to 1099, 2,000 to 2049, 2050. Oh my gosh, I can't even count. I'm sorry about that, guys. Okay, let's try 1,100, 1149. Goodness gracious. 1150 to 1199, 1200 to 1249. See, 1250 to 1299, 1300 to 1349. See, do we have to go a little bit further? Yeah, that's all of them. Okay, so there's my intervals. So now let's count up how many are in each interval. So 1,000 to 1049. I don't have any there. So actually I should probably make some marks here to say, okay, so 1, 2, 3, 4, 5, 6, 7, 8. Let's go with 8 for now. And if needs be, we will extend that. Okay, so there's none in my first interval. Let's see how many are 1050 to 1099. 1050, so here's 1, to 1099. It looks like we just got 2. So I make my bar up to 2. Okay, 1100 to 1149. Switch colors. 1100 to 1149. Okay, we got 1, 2, 3, 4. So 4 goes up to here. 1150 to 1199. One, two, three, 4 again. Okay, 1200 to 1249. 12 to 1249. One, two, three, four, five. Okay, so this bar goes up just a little higher. And then 1250 to 1299. 1250 to 1299. Okay, we got 3 there. And 1300 to 1349. I'll do that in blue, I guess. So we got 1, 2, 2. Okay, so take it down to. Okay, so there's my bar graph. What do you guys think? It looks pretty symmetrical. Okay, so that's my histogram. Okay, so continuing with that, here's my histogram again. Okay, notice theirs looks a little prettier than mine does, but that's okay. So what does this data reveal? What does this display reveal about the data? Well, it looks pretty symmetrical. We call this a bell-shaped curve. Okay, notice how it kind of makes a bell. Okay, and when it's symmetrical, we say it's bell-shaped. Data that's in this shape is said to have a normal distribution. Okay, we like data like this. Okay, that's what we expect to happen. We don't like skewed data. We want it to be normal. So when the data are normally distributed, the most useful measure of spread is called the standard deviation. Standard deviation is a measure that shows how data vary or deviate from the mean. Okay, remember, mean is my average. Okay, so here's my bell curve. We are talking about standard deviations. So we, in a normal distribution, we have up to about 3 standard deviations is what is expected. 68% of the data fall within 1 standard deviation of the mean. Okay, so this area right here that they have in the blue is plus 1 standard deviation on this side. Okay, this dotted line in the middle is the mean, and over here it'd be minus 1 standard deviation. Okay, 68% of the data is in between those 2 red lines. Then we move into 2 standard deviations. Okay, this time it's the orangey pink. The orangey pink, okay, all of this area. Okay, that includes 95% of the data. So from here to here is plus 2 standard deviations. From here to here is minus 2 standard deviations. And then finally, we have 3 standard deviations. About 99.7% of the data fall within 3 standard deviations. Okay, so that includes this whole area. Okay, so from the mean to here is plus 3 standard deviations. And then from the mean to here is minus 3 standard deviations. Okay, so basically, you calculate your standard deviation, and then you add it 3 times, and that gets you to this point. You subtract it 3 times, gets you to this point. Okay, that's what that is saying. Okay, 68% of the data is within 1 standard deviation, 95% within 2, 99.7 within 3. So let's look back at our curve. Okay, they calculated the standard deviation for us. Okay, the standard deviation for this sample is 75.5 hours. Okay, so we know the mean is 1200. So 1 standard deviation would be 75.5 hours more than that 1200, or 75.5 less than that 1200. So light bulbs with a span between 1000 to 124.5, so minus 75.5, and 1275.5, so plus that 75.5, lie within 1 standard deviation. In a large sample drawn randomly from among such light bulbs, we would always expect about 68% of the lifespans to be within 1 standard deviation of the mean. Okay, so 68% of my light bulbs are going to fall between those 2 values. Okay, so given that the average life of the light bulb is 1200 and the standard deviation is 75, what's the lifespan of light bulbs that are 2 standard deviations of the mean? Okay, so we'll look over here, 2 standard deviations, and then we're going to do 3 standard deviations. So I'm going to take 1200, I'm going to add 2 times 75.5. Okay, I'm going to throw that in my calculator real quick. 1200 plus 2 times 75.5. I get 1351. And I'm going to do the same thing, but now I'm going to subtract. Pull that back up. Subtract it. Oops, not plus, minus. 1049. So 2 standard deviations. So 95% of my data are between, let's see, 1049 and 1351 hours. Okay, so now let's look at 3 standard deviations. Same process, but instead of saying times 2, I want 3 standard deviations. Oops. Sorry, pen's messing up on me. Okay, so 1200 plus 3 times 75.5. I get 1426.5. And same thing, but now I'm going to switch to minus. And I get 973.5. So we know 99.7% of light bulbs are between 973.5 and 1426.5 hours. Okay, so we can almost guarantee our light bulbs are going to last 973 hours. All right, so that's the first one. So let's figure out how to actually calculate the standard deviation. So the table here shows the number of cars sold by an auto sales associate over an 8-week period. How much variability did the data show? Okay, so notice we have a kind of small sample size here, 1, 2, 3, 4, 5, 6, 7, 8. That's going to be nice. You don't want to do big ones like this by hand. So we're going to find the variability by solving for the standard deviation for a sample using the formula S equals the square root of the summation of x minus x bar squared divided by n minus 1. Okay, that formula looks worse than what it actually is. Okay, S, actually here, let me show you the next slide. S is your standard deviation. The weird E looking thing is called sigma, so Greek letter sigma. That means sum. Okay, so I'm going to add up everything I do in the parentheses there. X bar stands for mean, the average, and N is your sample size. Okay, so we're going to calculate each of these. Ready? Okay, here we go. So step 1, we need to find the mean. Okay, we know how to find the mean. Okay, and we're going to use X bar to denote this. So X bar, so remember, average, mean, you add up all the numbers. So 18 plus 25 plus 18 plus 10 plus 17 plus 15 plus 18 plus 15. And you divide it by the total number. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so divide that by 8. So that's some calculator work here. Plus 25 plus 18 plus 10 plus 17 plus 15 plus 18 plus 15 gives me 136. When we divide that by 8, we get 17. Okay, so I know X bar equals 17. Okay, so the next thing we're going to do, step 2, we're going to find the difference between each data value X and the mean. Okay, so I'm going to take each of these numbers and subtract the mean from them and then square it. So sometimes it helps to make a chart. So you can do X plus your values, X bar, which we know is 17 all the way across, and we're going to do X minus X bar. Okay, so we got a couple different things to do right now. So let me list the data: 18, 25, 18, 10, 17, 15, 18, 15. Okay, and I know x bar is 17 all the way across, so you can fill that out. You don't have to do this if you don't want to, but this helps. So now I'm going to do x minus x bar. 18 minus 17, 1. 25 minus 17, 8. 18 minus 17, 1. 10 minus 17 is negative 7. 17 minus 17 is 0. 5 minus 17 is negative 2. Or sorry, 15 minus 17. 18 minus 17 is 1. 15 minus 17 and negative 2. Okay, next column. We now need to square each of those. X minus x bar squared. So I'm going to take the red and square it. 1 squared, 1. 8 squared, 64. 1 squared is 1. Negative 7 squared is 49. 0, 4, 1, 4. Okay. Everyone's still okay there? Good. Now, we need to sum them up. Okay, that's what sigma means. So I just want to add up the column here and get my total. Okay, the total of the blue. I'm going to use my calculator because there's some big numbers there. So 1 plus 64 plus 1 plus 49 plus 0 plus 4 plus 1 plus 4. Yeah, 124. So what we just found there in blue is this part of my formula. Okay, so that's step 2. Step 3, they say find the variance. So the variance of a total population, often noted as squared, is the mean of the squares of the differences between each data value and the mean. So the variance is our formula, just not the square root. Okay, the variance is the summation of x minus x bar squared divided by n minus 1. That's what s squared equals. Okay, so to get s, we just square root. I think that makes sense. So we are working with a sample, so we divide by n minus 1. When we work with a population, we just divide by n. Okay, so when finding the variance of a sample, we divide by n provides too small of an estimate. Okay, it's because the data points from the sample are likely to cluster more closely around the mean than the population mean. So if you divide by n minus 1, we get a slightly bigger number that is closer to the true population. Okay, sample, you divide by n minus 1. So basically, there's a lot more information here than we need. We're just going to take step 2 and divide by n minus 1. So step 2, we take 124, and I need to divide that by n minus 1. Okay, n, remember, is the sample size. We know that's 8. So I need to do 124 divided by 8 minus 1, or 124 divided by 7, which equals 17.7. That is my variance. Okay, last step, you just take the square root. So I need to do the square root of 17.7. I get s equals 4.2. So my variance of this sample, or my standard deviation, is 4.2. So my numbers vary by about 4.2 from my mean. Okay, so again, formula one more time. S stands for standard deviation. Sigma is sum, means add it all up. X bar is your mean, and n is your sample size. Okay. So let's do another one. Okay, table shows the number of cars sold by the auto sales associate over the next 8-week period. How much variability did the data show? Okay, so again, remember S is equal to the square root, summation of x minus x bar squared divided by n minus 1. Okay, so we're going to repeat it. First thing we do, find the mean. Okay, so again, remember how to blow up. All right, so step one, find the mean. Now we're going to set up our table. Okay, so remember we did x, then x bar. Okay, so start my x's. Okay, x bar again, we just found that. I like to just fill it all the way out. Okay, now we want to do page. Drop some of these down a little bit more. Okay, I want to do x minus x bar. Okay, so 12 minus 16.5, negative 4.5, 14 minus 16.5, negative 2.5, 29 minus 16.5, 10 minus 16.5, 17 minus 16.5, 16 minus 16.5, 18 minus 16.5, 16 minus 16.5. Okay, then the next thing we do, we square those. Okay, so negative 4.5 squared gives me 20.25. Negative 2.5 squared gives me 6.25. 12.5 squared gives me a big number, 6.25. Negative 6.5 squared gives me another big number, 0.5 squared, negative 0.5 squared, 1.5 squared, negative 0.5 squared. Okay, and then we need to find the total. Okay, so add up all the blue. 20.25 plus 6.25 plus 156.25, 42.25 plus 0.25 plus 0.25 plus 2.25 plus 0.25. Big total 228. Whew. Okay. So now just need to finish it up. So we're going to take the square root of 228 divided by n minus 1. So we had 8 minus 1. Okay, so 228 divided by 7, and then the square root of that. So s equals 5.7. And there's your standard deviation. All right, so now so the next thing you want to do is find the population. Okay, the difference between a sample and a population. Sample is only taking part of things, okay, so drawing randomly. So like if I was thinking about my first period class, a random sample would be like picking Adam and Allie and Jaden and Caden, okay? Population would be my entire class, okay? Sample is taking part of the whole. So population is all of it. Okay, so table displays the number of points scored by a football team during each of their regular season games. Okay, so the population is all of the games. Sample could be like maybe just the home games. Okay, but this is a population because it is all of the games. Process is exactly the same. Okay, the only difference is since it is a population, we divide by n. Okay, not n minus 1. Okay, population, divide by n. Sample, divide by. Okay, that's the only difference. I'm not going to go through that because, again, the process is exactly the same except for that step. Okay, but same kind of thing. All right, now we're going to compare data sets using the standard deviation. So the histograms show the lifespans of a sample of light bulbs from two companies. The first shows a sample from brand A, the second from brand B. The red lines indicate the mean and each standard deviation from the mean. Compare the distributions of lifespans for the two light bulb brands. Okay, so this one here's my mean. Okay, this is 1200. Now we know my standard deviation is 75.5. So you can add 75.5 and subtract 75.5. Okay, that's how you get to these two red lines, and then you keep going. My second data, okay, here's my mean. Looks like it's about the same. And there's my standard deviations and where they are. Okay, so let's compare. So one standard deviation for my first sample was halfway in between 1100 and 1149. Notice this standard deviation is not. Okay, so it looks like brand B is a lot more spread out. So both brands of light bulbs have an average lifespan about 1200. Okay, we knew that. Standard deviation for the data set for brand A is less than the standard deviation for brand B. Okay, we notice that because look, it's a lot less space between each of the lines. Notice brand B, like I was just saying, we're a lot more spread out. Okay, so this suggests that brand A has less variability. Since light bulbs are more consistently closer to the mean, brand A light bulbs are more predictable. Okay, that's the interpretation here. We would like things to be predictable. We want the standard deviations to be smaller. Okay, so now let's look at compare brand C to both of these. Okay, so now we know that the standard deviation is 83. Okay, so this standard deviation okay, so I would say brand C is somewhere between brand B and brand A. We know it's 75.5 here, so A is still more predictable. 83 is a little bit bigger than that. It looks to me like it's a lot more than 83 in here, because this is 1200. This looks like it's about 1300. No, more than 1300. This standard deviation is over 100. So brand C is not as reliable as brand A, but more so than brand B. Okay, and that's what I have. So just to summarize, standard deviation is a measure of spread or variability. It indicates by how much the values in a data set deviate from the mean. It's also known as the square root of the variance. The variance is the average of the squared deviations from the mean. When data are normally distributed, so we want a bell curve, the mean and the standard deviation describe the data set completely. And remember, the formulas are almost identical. The only difference for a sample is you divide by n-1, population you divide by n. And again, remember here was our bell curve. 68% of the data is in between one standard deviation, 95% of the data is in two standard deviations, and 99.7% of the data is in 3 standard deviations. Homework tonight, you're on page 493. You're doing problems 9, 10, 13, 16 through 18. I did not put very many actually calculating the standard deviations on here because I know it's tedious. Okay, so please make sure you work those out. As always, if you have any questions, please let me know. Hope you guys have a great day.